Have you ever wondered what could happen if a spacecraft looked at a completely ordinary asteroid and found a world that should not be there? Because NASA's Lucy mission made a routine stop in deep space, and the object waiting in the darkness turned a simple test into a warning. Our solar system may be far more complicated than our maps suggest. Before we follow Lucy into that mystery, tap like, subscribe, and share this video. Share it with someone who thinks asteroids are just boring rocks. By the end, you may never look at a small piece of space debris the same way again. The most important discoveries do not always happen at the destination. Sometimes they happen during the quiet stretch of the journey. This occurs when a spacecraft is only checking its equipment and nobody expects a headline. That is exactly what happened to NASA's Lucy. Lucy launched on October 16, 2021 from Cape Canaveral. Its official mission is enormous and designed to explore the Jupiter-Trojan asteroids. These are two giant groups of objects that travel around the Sun along with Jupiter. One group moves ahead of the planet while the other follows behind. Jupiter's gravity holds them in remarkably stable regions of space. NASA plans for Lucy to visit 11 asteroids during a journey lasting about 12 years. It will travel billions of miles, use Earth gravity assists, and examine objects that no spacecraft has ever visited up close. These targets are not random stones chosen from a catalog. They may preserve material from the early solar system, including clues about where planets formed. They might show how planets moved and how the ingredients of Earth were distributed. The name Lucy carries its own message. It comes from a famous fossil discovered in Ethiopia in 1974, the skeleton of an ancient human ancestor that helped scientists understand our own origins. The spacecraft has a similar purpose on a much larger scale. Instead of studying one species, it is studying the beginning of an entire planetary system. But before Lucy could reach Jupiter's orbit, mission planners noticed that its path would bring it near a small main belt asteroid. The object was called Dinkinesh. It was not one of the mission's original headline targets. It was added as a useful opportunity. It was a chance to test Lucy's instruments and guidance systems before the spacecraft reached the more distant Trojan asteroids. That sounds reasonable. You do not test a new camera on the most difficult assignment of its life. You point it at something nearby. You check that it can track a fast-moving target, make sure the spacecraft can turn correctly, and then continue toward the main event. Dinkinesh looked like the perfect rehearsal. It was small, dark, and located in the main asteroid belt between Mars and Jupiter. From Earth, it appeared to be an ordinary object. There was no obvious sign that it was hiding anything extraordinary. On November 1st, 2023, Lucy flew past Dinkinesh at high speed. The encounter was brief. Lucy did not enter orbit around the small rock. It raced by, gathered images and measurements, and continued along its route. The team expected useful technical data. They perhaps expected a better understanding of a modest asteroid. Then the first images arrived. Dinkinesh was not alone. A smaller companion was moving around it. The asteroid had a moon. The discovery was already a surprise. The companion had not been detected in the earlier observations used to plan the encounter. But the real shock came when scientists studied the shape. They looked at that companion more carefully. It was not a simple round moon. It was made of two separate bodies touching each other. The companion was named Selim. Scientists call an object like this a contact binary, meaning two bodies that came together slowly. They moved slowly enough to remain intact rather than exploding apart. Imagine two rough piles of gravel drifting together under weak gravity. They collide gently, settle into contact, and stay joined. They are separate objects, but from a distance, they can look like one strange body. Selim was the first confirmed contact binary satellite ever observed around an asteroid. That sentence matters because space exploration has seen variety. Probes have visited planets, moons, comets, and many asteroids. They have found mountains, ice, dust, cliffs, craters, and jets. They have found landscapes shaped by impacts. Yet this particular arrangement had never been confirmed before, a double-lobed object orbiting an asteroid. The answer appears to begin with Dinkinesh itself. Images showed a long trough running across part of its surface and a ridge around its equator. Those features are not random decoration. They are evidence of motion, loss, and rearrangement. Asteroids do not need a giant collision to change. Sunlight can slowly alter their rotation. The effect is known as the Yarkovsky-O'Keefe-Radzievskii-Paddock effect, usually shortened to YORPY. It is subtle, but over long periods, it can make an irregular asteroid spin faster and faster. Why would light change a rock's spin? Because an asteroid absorbs sunlight and later releases heat. Its shape, surface texture, and rotation determine where that heat leaves the surface. The escaping thermal energy produces tiny pushes. They are far too weak to notice on a human timescale, but millions of pushes change the rotation. Eventually, a small asteroid may spin so quickly that material near its equator is no longer held tightly enough by gravity. Loose rocks can lift away. A larger section can break off. Some debris may fall back. Some may form a ridge. Some may enter orbit. That seems to be what happened at Dinkinesh. The trough may mark where a significant piece separated. The ridge may record material that shifted. Other fragments may have gathered around the asteroid, eventually forming the two bodies that became Salem. That changed the mood of the mission. If an unplanned stop could reveal a never-before-seen kind of satellite, what might Lucy discover when it finally reached the Trojan asteroids? There was another problem with the old assumptions. Before Lucy arrived, many small asteroids were treated as simple pieces of rock. Their size made them seem less important than planets or large moons. But Dinkenish showed that small does not mean simple. A body that looks like a dot through a telescope may have a complicated interior history, active rotation, and material lost to space. It may have a companion assembled from its own fragments. The lesson was already powerful, but Lucy was not finished with its warm-up journey. Its next major encounter was with an asteroid named Donald Johanson. The name honors the paleoanthropologist associated with the fossil Lucy. The connection was intentional. The spacecraft named for the fossil would visit an asteroid named for the scientist who found the skeleton. On April 20th, 2025, Lucy passed Donald Johanson at a distance of roughly 600 miles, or about 960 kilometers. The spacecraft was moving at close to 30,000 miles per hour. At that speed, even a small targeting error matters. The encounter window was short, and Lucy had to operate with remarkable precision. From Earth, scientists noticed the brightness changed. It changed over a cycle of about 10.5 days. Brightness changes often reveal that an asteroid is elongated and rotating, so the basic expectation was simple. Lucy would approach a stretched, irregular body, photograph its surface, and measure its composition. But once the images began returning, the shape was stranger than expected. Donald Johanson is bilobed with two major sections joined. They are joined by a narrow region. It resembles a peanut, but that comparison does not fully capture its geometry. The connection between the lobes has a sharply unusual shape, and the surface contains craters, ridges, and textures from impacts. These are geological changes produced over time. The asteroid is about 8.8 kilometers long and about 4.4 kilometers wide. It is not a smooth object. It is a record of a collision in the distant past when a larger parent body was destroyed. Its fragments began moving through space. Here is where the story becomes more surprising. Donald Johanson did not appear to be a fresh pile. It was not a violently shattered pile whose pieces were still flying away. The two main sections had likely drifted back together. They met slowly enough under their mutual gravity to merge without completely breaking apart. It is aftermath, followed by reunion. A parent body was broken, its pieces separated. Then two of those pieces found each other again and became one object with a visible scar. That alone would make Donald Johanson valuable. But Lucy detected something that made the asteroid even more important. It was not simply spinning around one stable axis. Most people imagine an asteroid rotating like a ball or a top with one clean axis. They expect one predictable motion. Donald Johanson does not move that way. It rotates end over end in about 10.5 days. It also wobbles around another axis in a cycle of about 26.5 days. This is called non-principal axis rotation. It tumbles. Its movement is more like a badly thrown football than a carefully balanced top. The body is rotating and wobbling at the same time. This produces a motion that is difficult to picture until you see a model. Why is that important? Rotation tells us about structure. It tells scientists about history. A stable asteroid tends to lose complex motion over time through internal friction and other processes. If Donald Johanson is still tumbling, something about its shape, mass distribution, or past collision allowed that unusual state to survive. The asteroid's two lobes may be part of the explanation. A stretched, uneven body does not behave like a sphere. Its mass is distributed irregularly. When fragments merge, they may preserve angular momentum that never settles into one simple spin. The result is a body that carries the memory of how it was assembled and the way it moves through space. Lucy's infrared instruments detected iron-rich clay minerals on the asteroid's surface. Clay is not just dust with a scientific name. On rocky worlds, clay minerals can form when liquid water interacts with rock over time. The chemistry changes and minerals are transformed. The final material preserves evidence that water once moved through the original body. This does not mean an ocean was flowing there today. It does not mean the asteroid is wet today. It means the parent material experienced an episode of liquid water alteration. That is a remarkable result for a small body in the main asteroid belt. Donald Johanson itself formed after a collision. This happened about 155 million years ago. Its parent body must have existed before that event with liquid water inside it. The timing and chemistry matter. Liquid water inside a small rocky body is not easy to maintain because space is cold. Small objects lose heat quickly. A body with weak gravity cannot hold a thick atmosphere like Earth. Scientists ask where heat came from. Possible heating sources include radioactive elements in an earlier parent body, impacts, or chemical reactions. Scientists must compare the mineral evidence with models of asteroid formation and evolution to find the true story. The answer is not simply there was water. The deeper question is how a brief water-rich environment could exist in a dry place. This is also connected to one of the biggest questions in planetary science. Where did Earth's water come from? Earth formed relatively close to the Sun, in a region that was too warm for large amounts of water ice to remain. Yet our planet has oceans, groundwater, glaciers, and water locked inside minerals. Some water may have been present in Earth's ingredients, but impacts from water-bearing asteroids and other bodies are an important part of the story scientists investigate today. If water-altered material existed in the asteroid belt, then the neighborhood around the young Earth contained more diverse material. Water did not have to come only from the farthest regions of the solar system. Rocky bodies closer to Earth may have carried it. They may have stored or transformed water-bearing ingredients. That does not solve the origin of Earth's oceans entirely. It adds a new piece to the puzzle. It tells us that the routes by which water and minerals moved were complicated. There was no neat division between dry inner worlds and icy outer worlds. Dinkinesh and Donald Johanson are different objects. One has a tiny contact binary satellite formed from material that separated. The other is a tumbling, bilobed asteroid. It has evidence of ancient water-related chemistry. Yet they share a deeper pattern in their complicated histories. Both were assumed to be limited. Both turned out to have multiple layers of history. Both showed size tells us almost nothing. An asteroid's size does not dictate how interesting it may be. This is why close flybys matter so much to NASA. A telescope can tell us brightness, color, approximate size, and orbit. Those measurements are powerful but limited. They cannot always reveal a narrow neck, a surface trough, a hidden satellite, or mineral signatures that point to water. To see those details, a spacecraft has to cross the distance and look directly. And the mission's central targets are still ahead. Lucy's first Trojan asteroid encounters are scheduled for 2027. It will later visit additional targets, including Trojan groups. These asteroids occupy gravitationally stable regions associated with Jupiter. Many believe they preserve material from a very early period. The Trojans could help test competing ideas about planetary migration. Did the giant planets form where we see them now? Did Jupiter and Saturn shift positions early in the solar system's history? Were some Trojans born near Jupiter or captured elsewhere? Were they caught during a chaotic rearrangement? Every Trojan Lucy visits may provide a different clue to these questions. Some may be dark and carbon-rich. Some may contain hydrated minerals. Some may have satellites or be binaries. Some may have surfaces shaped by collisions that occurred billions of years ago. The diversity of the targets is part of the design. Lucy is not going to one asteroid and assuming it represents everything. It is visiting a family of objects, then comparing them. That comparison can reveal which features are common and which are unusual. It can show whether Trojan asteroids share a birthplace. It can show if they were gathered from different regions during the system's early upheaval. This makes the mission a time machine. It is a time machine in a scientific sense, though not in the science fiction sense. Lucy will not travel backward in time. It will inspect ancient material that has survived with less geological change than the major planets. Earth recycles its surface constantly. Weather, erosion, volcanism, plate tectonics, and biology change Earth. Asteroids do not have the same machinery. Their surfaces can preserve older records. But the word preserve should not fool us into thinking asteroids are frozen and inactive. Dinkinesh changed its shape through rotation and mass loss. Donald Johanson carries a collision history and a complicated motion. Small bodies evolve. They collide, fracture, spin, shed material, and merge. The important difference is that changes remain visible. A ridge may reveal that an asteroid once spun faster. A contact binary may show that fragments reunited later on. A rotation state may expose an uneven interior. A clay mineral may point to water in a vanished parent body. None of these clues stands alone. Scientists combine them like pieces of a case that began billions of years ago. This also explains why headlines about NASA stopping the world need a little caution. The discovery did not literally stop rotation. It did not shut down every observatory or overturn every law of physics. The phrase captures the emotional effect of results. What changed was not the planet. It was the confidence of the models used to describe small asteroids in space. Science does not move forward because one image proves everything else worthless. It moves forward when limits are exposed. The old ideas may still work in many situations, but they need to become more precise. A model must account for hidden satellites. It must account for contact binaries, rapid spin evolution, complex tumbling, and water-altered minerals. These are the new rules. The first valley contained Selim orbiting Dinkinesh. The second contained Donald Johanson tumbling with mineral evidence of water. The discoveries are visually dramatic, but their real importance is deeper. They connect motion, chemistry, and history together. Consider Salam's formation. Sunlight may have changed Dinkinesh's spin. A piece may have separated and debris entered orbit. Two fragments may have formed and eventually touched. A single asteroid became a primary body, plus a complicated satellite. That change shows how small gravitational systems can build structures without a planet-sized world or a powerful atmosphere. Now, consider Donald Johanson. A larger parent body was destroyed. Fragments moved apart and two pieces later reunited. Their uneven shape affected their rotation. Their motion preserved information about their assembly. Minerals recorded liquid water. This water belonged to an earlier stage of the family's history. These are not isolated oddities. They are examples of complexity. Rock, sunlight, gravity, heat, and time can produce bodies that look almost designed, even though no designer was needed. There is another human detail in this mission that is easy to miss. The name Lucy was chosen because of a fossil. Donald Johanson was named after the scientist connected to that fossil. Dinkinesh and Salem were given names connected to the same story. The mission's naming system links two kinds of discovery: learning where we came from as a species and as a planet, and the surprises may continue. Lucy is now carrying the lessons from its first encounters toward unexplored regions of space. The instruments have been tested on real targets. The navigation team has practiced the difficult timing. The scientists know the truth. They know an ordinary asteroid can hide a companion, a strange rotation, or a chemical record of water. Here's the human moment. Every image from Lucy began as a question, crossed millions of miles, and ended in someone's hands on Earth. If that journey means something to you, share this video and stay with the mission. If this journey changed how you see asteroids, let your support travel with Lucy. Leave a comment with the strangest space discovery you have ever heard of, and subscribe. Subscribe so we can follow the next reveal together. Your curiosity is part of the mission too. Quick mission check now. If you thought the asteroid belt was just cosmic gravel, hit like for the plot twist and subscribe for the next flyby. Share this with the friend who always says space is empty. When the images arrive, they may be compressed or incomplete. They are captured under difficult lighting. Scientists have to work with shadows, angles, changing brightness, and uncertainty. They compare several frames. They calculate how features line up. They test different shapes and rotations to find the fit. They look for explanations that fit all the evidence rather than one exciting picture. That is why a scientific discovery takes time. The spacecraft may finish the encounter in minutes, but the interpretation can continue for months or years to get it right. The first view reveals the surprise. The analysis reveals what the surprise means. It is tempting to say Lucy found water. The accurate statement is that Lucy found mineral evidence consistent with a past episode of liquid water alteration. Wording matters. The wording respects what the data can actually show. Look again at the word small. It often describes size as importance. Dinkinesh and Donald Johanson prove that is a dangerous shortcut. Small worlds can have satellites and break apart. They can rebuild. Small worlds can preserve the chemical consequences of water. Their histories are compact but enormous in meaning. The same principle applies beyond space. A small clue can overturn a large assumption. A faint signal can reveal a hidden system. A detail that seems unimportant can become the key to understanding the whole structure. Exploration rewards attention. Lucy's story reminds us that discovery is not always a dramatic collision caught at the perfect moment. Drama is in the reconstruction. A rock has a scar. A companion has two lobes. A surface contains a mineral. A rotation repeats on different schedules. Scientists connect those details and recover events that happened billions of years ago. It is almost like solving a crime scene. Witnesses are gone and the evidence has been exposed to space for ages. There are no voices and no obvious narrative. Only shapes, temperatures, minerals, orbits, and motion. The spacecraft gathers the evidence. Human beings build the explanation. Unlike a fictional mystery, the explanation must survive testing. Another scientist must be able to examine the observations. They must challenge the assumptions. That process turns a surprising image into reliable knowledge for everyone. NASA's Lucy mission is still active, and its target list extends far beyond these first two encounters. It will visit Euripides. It will visit Keta, Polymele, Lucas, Orus, and the binary pair Patroclus and Menoetius. Each flyby will add another comparison. The most valuable target may not be the largest. It may be the one that breaks a pattern. If Trojans differ, that reveals origin. The spacecraft may find moons, unusual shapes, active processes, or signs of distant material. It may find objects that match models. That would matter too. A theory becomes stronger when it survives a fair test in the deep darkness of space. Either way, Lucy is giving scientists something they could not obtain from Earth alone: direct evidence from a new population. Dinkinesh showed an archive entry hidden in an ordinary name. Salam showed that a satellite can have its own complexity. Donald Johanson showed an asteroid can tumble and carry water-related minerals. The discovery stopped us for a moment. It made us pause and reconsider the picture in our heads. We imagined the asteroid belt as a ring of lifeless rubble. Close-up observations reveal a place full of motion, history, and chemistry. Sunlight can change their spin and gravity works. We imagine water belongs to oceans, but minerals preserve fingerprints. A small rock carries a record of events before Earth was home. That is the real power of Lucy. It is testing whether our picture of planetary history can withstand contact with reality. So far, reality has been more complicated. A A test target revealed the first confirmed contact binary satellite around an asteroid. Another revealed a peanut-shaped body with two-axis tumbling in clay linked to water. These findings came early in the mission. Imagine the spacecraft arriving at Jupiter's neighborhood where objects preserve materials from a completely different region. Imagine the first close-up image of a Trojan no human has ever seen. Imagine a surface that does not match the models. Imagine a hidden companion or a mineral signature that points to a new migration route. We cannot know which surprise is waiting. That uncertainty is the reason to go. The best missions are carefully built questions sent into places where answers challenge us. Lucy is one of those questions. When it reaches its targets, the images may arrive as small, imperfect frames on computer screens. But inside those frames could be evidence about Jupiter's early history and the movement of giant planets. A distant rock may tell us more about our home than another picture of Earth ever could. Lucy looks at the smaller pieces. The fossil that gave Lucy its name helped us understand our past was different. The spacecraft repeats that on a cosmic scale. It goes looking for confirmation and finds complexity instead. Dinkinesh says, even a modest asteroid may have a hidden family. Donald Johanson says a shattered world may preserve chemistry and move in ways we cannot predict. Never confuse distance with simplicity. Space is not quiet because nothing is happening. It is quiet because events are slow and ancient. Gravity pulls and sunlight heats. Millions of years later, a spacecraft passes by and notices. Lucy has shown that the solar system is full of layered histories. The main show has barely begun. The next time someone calls an asteroid just a rock, ask them what kind of rock it is. Is it a survivor of a destroyed world? Is it spinning fast? Does it have a hidden companion? Does it have water fingerprints? From far away, we see a dot. Up close, we see a family and a clue about Earth. If you want to see more, subscribe now. NASA's Lucy discovery showed exactly where our rules are incomplete. It reminded us the universe is not obligated to be simple. Every new target will be examined with sharper expectations and greater humility. The discovery may hide in the object nobody thought would matter. Somewhere ahead, an ancient Trojan asteroid is waiting in the sunlight, carrying a story that has survived since the birth of the planets. When Lucy finally looks closely, humanity will get its first real glimpse. The image may be beautiful or confusing, but worth the wait. Because every time we travel farther, the universe gives us less certainty and more truth about our place in the cosmos.